Hey folks, it's time for another video lecture from Mr. Bryant. This one is going to be on an object's center of mass and its moment of inertia. I'd like you to do a very quick experiment for me, one that's similar to the one I conducted in class today. Get out a pen or marker or some other implement that has a cap on it and toss the object into the air. Watch to see how the object rotates. Then remove the cap and repeat the procedure. Is there any difference in how the object rotates? That is there any difference in the point within the pen or pencil that changes as the object rotates when you have the cap on or the cap off? There should be a difference. Putting the cap on the pen or pencil ends up changing where its center of mass is. It makes it so the pen or pencil is no longer something that is uniform. That is, something that has a symmetrical shape with an even distribution of mass. You can experience this phenomenon if you're one of the kinds of people, like me, that can spin a pen or pencil around your fingers. When you take the cap off, it should spin around its geometric center. The term for the point around which an object rotates is called its center of mass. Again, for uniform objects, the center of mass is also at its geometric center. For a system like two objects that are orbiting around each other, like two stars, center of mass will be at the geometric center if the two stars have equal masses. As we start to imbalance our system, in this case, as we have one star that's more massive than the other, the center of mass moves toward the more massive object. In the case of a significant disparity in mass, say with the sun compared to any planet going around it, the center of mass is extremely close to the geometric center of the sun itself, due to the extreme differences in mass between the two objects in the system. If you let an object rotate, say for example the planet to rotate around its own axis, or for a ruler to rotate as it rotates through the air, it will move around its geometric center. Let's say for example, if you rolled a ball down an incline, it would roll around its axis, or a line drawn through its center. This is going to have important implications once we start doing problems involving an object's center of mass and its gravity exerting torque on the object. So when we do problems in particular that involve multiple forces and multiple torques, that's when we're going to have to worry about where an object's center of mass is compared to the point around which where the object would rotate. So here we have a cow on a diving board. We have two things that are exerting downward torque on the diving board: the diving board's own weight and of course the weight of the cow. So let's say for example we had a diving board that is 2 meters long and has a weight of 120 newtons. This would be exactly the same thing as if we had someone pushing on the diving board at its exact geometric center with 120 newtons of force. For this diving board, its geometric center would be at 1 meter from either end. So here's the problem. You can try to work this yourself, or you can just listen to me and follow along as I set it up for you. I give you in this problem the weight of the cow. I tell you it's a 3 meter long diving board, which means that if we're going to assume this is something that is uniform, its weight would be concentrated 1.5 meters from either end. The cow is standing 2.5 meters from the point around which the board would normally rotate. We have also attached a support that will act 0.3 meters from the base. This support is going to be the thing that exerts upward torque and prevents the diving board and the cow from rotating. So the cow has a weight of 640 newtons, and what I expect you to do in this problem is take the information I've given you and figure out how much torque the support will have to exert to keep the system in equilibrium. The key here again is that the support is exerting all of the upward torque here. So it has to counteract the torque of both the cow and that exerted by the diving board's own weight. So if we set up the problem, the torque exerted by the support minus the torque of the cow minus the torque of the board's weight must equal 0. I'm subtracting the torque of the cow and the board's weight from the support because those two forces combined and those two torques combined must equal the torque of the support. So when I look at the formula below on the bottom of the screen for the torque exerted by the support, the length of the lever arm is going to be 0.3, since I said it was 0.3 meters from the location where the board would like to rotate, times the sine of 90 degrees, minus the torque exerted by the cow. The cow will exert a force equal to its weight, times the length of its lever arm of 2.5, times the sine of 90. The board will exert a torque equal to its weight of 640 newtons, the length of its lever arm of 1.5, and the sine of 90 degrees. Again, remember that the weight of the board is considered to be concentrated at its geometric center. And since we're talking about the distance from that geometric center and the point of rotation being our lever arm, it's just 1.5 meters. So we add up our known values for torques, and the force exerted by the support times its lever arm must equal the torques exerted by the other two objects. We get a force exerted by the support of 18,200 newtons. Here's a problem for you to try by yourselves. You may want to try drawing this before you attempt to solve it. We have a drawbridge with a mass of 300 kilograms extending straight out from the front of a castle. There is a chain holding up the drawbridge that makes a 50-degree angle with the drawbridge itself. We're trying to figure out the upward force exerted by the chain. I tell you specifically that the chain is attached at the far end of the drawbridge, which means that the lever arm in this case will be the entire length of the drawbridge, or 6 meters. We also have a person standing on the drawbridge, which will exert a downward torque on it. The key here, again, much like the previous problem with the cow and the diving board, is that we have one object, in this case the chain, exerting all of the upward torque in the system. We have a downward torque being exerted by both the person and the drawbridge's own weight. Try to solve this problem yourself, and then move forward with the answer when you're ready. So we enter our values for what we know. The chain will have a lever arm of 6 meters since it's attached from the end of the drawbridge, and the other end of the drawbridge is the point around which it will pivot. We'll use the sine of 50 degrees since it makes a 50-degree angle with the drawbridge itself. The torque exerted by the drawbridge will be its weight, mass times acceleration due to gravity, times its lever arm, which will be 3 meters. Again, note that that's the geometric center, and in this case, the geometric center is exactly the distance between the point of rotation and the center of mass for the object. We will subtract from that the torque exerted by the person, which will be their weight, times their distance from the center of rotation, times the sine of 90. And much like before, we add up the torques that are trying to rotate the system down. That must equal the torque exerted upward by the chain. We divide that by the product of the lever arm and the sine of 50 degrees. We get a force exerted by the chain then of 2,350 newtons. At this point, the part of the presentation required for my CP kids is done. So if you want, you can stop right here. If you're the honors kids, you have to keep watching this and get through the material on moment of inertia. Of course, if you are one of my CP kids and you want to keep going on, then please, by all means, you will have to watch this at some point anyway. For all of you who are going to continue, you're going to need to do a little experiment for me. I want you to get two objects, both of which need to be round and can roll. Get one that's hollow, say an empty soup can or a tennis ball or even like an empty soda bottle, something like that, and one that's solid. You could have a golf ball or a full soup can or what have you. Then I want you to set the objects at the same height on some kind of incline. If you have to, make the incline yourself by, say, propping up a book or something like that and letting the objects roll. Be sure that you release them at the same time. You should notice that one of them rolls much faster than the other when it gets to the bottom in a much shorter amount of time. What you've just experienced by doing this little experiment is a property of matter called moment of inertia. Moment of inertia is sort of like what mass is for the problems that we've done before, just involving linear forces. When an object is more massive than a second object, it takes more force to accelerate that first object at the same rate as the second. For a rotating object, moment of inertia represents how difficult it is to get that second object to change its state of motion. The greater an object's moment of inertia, the more effort you're going to need to use to get that object to either speed up or slow down. Here we see a couple of different formulas for an object's moment of inertia. Actually, solving for moment of inertia is kind of a pain. So what I've done is just presented a diagram showing the moment of inertia for different shapes that may exhibit rotational motion. If you see, for example, on the lower left-hand corner of the picture that I've put up there, you'll see the moment of inertia for a solid disk or cylinder that's spinning around its axis. This is what you might see, for example, in a record player. Over on the right-hand side, you see the moment of inertia for a solid sphere rotating about its diameter. This is how you would calculate the moment of inertia for something like a rotating planet. Below that is the moment of inertia for a thin spherical object. This would be like if you were trying to make a basketball make a circle on your finger or rotate on your finger, which, of course, I can do because I am totally sweet at hoops. So if we look at the two objects there, the solid sphere and the spherical shell, which one has the greatest moment of inertia? Take a moment to look at it, stop the presentation, and move on when you're ready. Obviously, the one that has the greater moment of inertia is the thin spherical shell. Its value is 2/3 times its mass times its radius squared, where the same value for the solid sphere is only 2/5 times its mass times its radius squared. So all other things being equal, if we had a solid object and a hollow object that were both round, both had the same mass and radius, the thin object, or the thin spherical object, would have a greater resistance to a change in its state of motion. This is why the solid object should have won the roll-off that you had. It has a lower resistance to a change in its state of motion. So if you think about it in terms of what the two objects are going to do when you let them roll freely, both of those are going to be acted on by the force of gravity, and are probably acted on by similar frictional forces as well. Shouldn't be too much different between the two objects. That means the object that has the lower resistance to a change in its state of motion should start rolling faster than the object that has the greater resistance. Another way of looking at this, and to tie it into stuff that we learned with linear quantities, is that imagine you had to push your friend's car out of a ditch. You would much rather have that car, say, have a mass of 500 or 600 kilograms, be like one of those smart cars, than have to help your friend push a Hummer out of a ditch, something that has a mass of probably several thousand pounds, or a weight of several thousand pounds, and a mass of at least 1,000 kilograms. The same principle applies here. For an object to accelerate in rotational motion, for us to exert the least amount of effort, we want a majority of its mass concentrated around its rotational center.